Okay, so using identities. And as I said before, identities can be used to simplify and prove trigonometric expressions. And this is going to be way easiest to see through a series of examples. So let's say we have cosecant x over sine x, and that's added to secant x over cosine x. Is there any way of combining these fractions together and seeing if we could come up with another expression for this that would be equivalent? Well, there are ways to do it. Most of the ways that we will be working with will rely on this main hint. And that's to put everything in terms of sine and cosine. So cosecant, well, that's 1 over sine, and secant is 1 over cosine over cosine. And to add and subtract fractions, what I really need to do is come up with a common denominator. And so this one would multiply by cosine on the top and cosine on the bottom. And this one would multiply by sine on the top and sine on the bottom. And so I will get an expression that will look a little bit more, well, the denominator is now sine x times cosine x, and the numerator is still a bit complicated, but I get cosine x over sine x plus sine x over cosine x. And I've done a pretty hard example to start with, just so you can see that a lot of these times we're going to be working with fractions within fractions, and they do get a little bit complicated. But if we essentially ignore the bottom now and just keep it the same, I just need to add fractions on the top. And again, I need a common denominator between them. So I'll use a different color, but this fraction needs to have a denominator with cos in it. So I'm going to multiply the top by cos and the bottom by cos. And this fraction needs a denominator with sine in it. So I'm going to get sine on the top and sine on the bottom. And I'll just work across the page here. So these were equal to each other. And now on this numerator I get cos squared x. And that's going to be added to sine squared x. And all of that is divided by sine x cos x, and all of that is divided by sine x cos x. You will be using quite a bit of space to write all of your steps down with these, so if I create myself a little more space here, I can start to see other trigonometric identities creeping in here. Cos squared x plus sine squared x, that's the same as sine squared x plus cos squared x, which is 1. And 1 over sine x cos x gets divided by sine x cos x. And division is the same as, so there's the first part, timesing by the reciprocal. 1 over sine x cos x. And so 1 times 1 is 1. Sine times sine is sine squared, and cos times cos is cos squared. And that's about as simplified as I'll go with this one. There's a few other steps I could do. For instance, I can say, okay, well, 1 over sine squared, that's the same as cosecant squared, and 1 over cos squared, that's the same as secant squared. So there's lots of other little manipulations that I could do, but these expressions are both equivalent to the original expression. In fact, every line that I've done is equivalent to the line above and below it. So these are all equivalent. And I guess a little challenge question for you is, how could I prove that that first line is equal to the second line is equal to the third line without using algebra? What ways would prove to you, for instance, that that expression is exactly the same as this expression, but I don't use any algebra at all? And it's a bit of a tricky answer, but maybe if someone reminds me, we can start with that in class on the first look at this stuff. Okay, let's try a couple more examples and just see how some other things can simplify. So this one's secant x over tan x. This one's actually much easier to work with. Again, I did a more complicated example first, just to get used to the algebra. But if you change everything to sines and cosines, then this becomes 1 over cos, and tangent becomes sine over cos. And you can do some manipulation, like multiply the top and bottom of the fraction by cos. And so you get 1 over sine. And 1 over sine is cosecant. And that one simplified quite nicely. But what we're getting at here is that you can rearrange these formulas, secant x over tan x, that expression, to become a simpler expression or a different expression, cosecant of x. And if I took one like secant squared x minus 1 times tan x, no, let's not do tan x. Let's do cotan squared x. We can play around with this one and see if we can come up with a different expression that's equivalent to it. And I'm going to do this one in a couple of different ways. So here's secant squared x minus 1 and cotan squared x. So if you go back to, everything into another form of sines and cosines, then this becomes 1 over cos squared minus 1, and this becomes cos squared over sine squared. And to add and subtract numbers together, fractions, I need a common denominator, so the denominator is going to be cos squared. This one needs to be cos squared over cos squared, and that's going to become times cos squared over sine squared. Oh, how convenient. There's a cos squared here and a cos squared here that cancel each other out quite nicely. Oh, and wait a sec. Sine squared x and cos squared x is equal to 1, so cos squared x is equal to 1 minus sine squared x. That's the Pythagorean identity, and I'm allowed to manipulate it around. So 1 minus sine squared, I could also manipulate it to become, instead of this, I can manipulate it to become 1 minus cos squared x, so move the cos squared x to the other side, and that would be sine squared x. So really, these are all equal, and I could take this one and make it into sine squared x, and that's over 1, and this is 1 over sine squared x. Wait a sec, this is fantastic. Those cancel, and I get a grand total of, this expression should be worth 1. Wow, that simplified really nicely. Let's take a look at this one, secant squared x minus 1. Oh, wait a sec, don't we have a Pythagorean theorem for that? So if you check back in the notes, this part here is equal to tan squared. And tan squared x times cotan squared, these are reciprocals of each other. So tan times cotan all cancel out. So it does work changing everything to sines and cosines, but sometimes it's faster to know the trigonometric identities and be able to plug them in. Sometimes you have to be able to plug them in as well to work through these things with a little more speed and accuracy. Okay, that's it. We'll see you in class.